Good morning, everyone. Welcome back. Hope you had a good weekend. Where we are today is we are just finishing up section 15.3. And this is the section on double or multiple integrals or double integrals in polar regions. So we're going to wrap up with this last example, and then we're going to get into section 15.4, which is on some applications of double integrals. So we'll see how double integrals get used in other areas of science. And then after that, we're not today, but next day, we're going to get into triple integrals. So the idea is with triple integrals, we are just basically extending what we've done from calculus 2 to now, where we went from 1 integral to 2. We're just going to continue on and see what multiple integrals can actually be and how to go ahead and calculate with them. So let's have a look at this final example. We've got a region that's bounded between a couple of surfaces, and we're interested in finding the volume. So we want to find the volume of the solid above the cone. Z equals square root of x squared plus y squared. So let's get a sketch of this thing. So we've got a cone. Maybe I'll change the color for the cone. So our cone looks something like this. Well, I won't fill in the top of it just yet because we don't know how far it's going. So there's our cone, which is going up. And we want it to be so above this cone and below the sphere. So we got a sphere as well. Sphere centered at the origin of radius 1. So we've got a sphere that's sort of coming down like this. And so on around. Now we're only interested in what's going on above the cone and below the sphere, so I can get rid of some of this stuff on the sphere outside this region. And so then we'll just focus on the part of the sphere that's sitting above the cone. So it's like this spherical cap that's sort of sitting there. And that's the region that we want to find the volume of. It's sort of like an ice cream cone. We got the cone and then the ice cream sort of ball or part of a sphere up top. So the couple of items to keep in mind are that's a sphere, x squared plus y squared plus z squared equals 1. This bottom portion's the cone, which is z equals the square root of x squared plus y squared. And in order to find the volume of this thing, we can look at it as two different pieces. We can look at it as the volume underneath the sphere between the x, y plane and the sphere. And then we could take away the volume under the cone of the under the cone above the xy plane. And so if we look at the difference of two regions, then we can see it as a volume computed by two different integrals. So one thing I'm going to draw in here is I'm going to say, okay, I'm interested in what's going on under the sphere above this cone. So in some sense, I'm looking at what's going on above this region in the xy plane. So we've got this circular region there, which is coming from the intersection. So let's look at what the intersection is. The intersection of the two surfaces. So that's this bit up here. We've got this plane, which looks like they are intersecting in. And the intersection curve looks like it's going to be this circle. And that's the circle that I'm essentially drawing down below. That's sort of the projection of that circle down into the xy plane. So what is this intersection? Well, we want to see when these two surfaces have common points. So we've got an x squared plus y squared plus a z squared, but z is given by a square root of x squared plus y squared from the other curve, or sorry, from the other surface. So what we get is that if x and y must live on, x, y, and z must live on both of these surfaces, then it's got to satisfy this equation. And so that means that x squared plus y squared has to be a half. And we also then get that z has got to be 1 over root 2. Okay, so just to get that first x squared plus y squared equals a half, we just square that square root and we get 2x squared plus 2y squared equals 1. So x squared plus y squared equals a half. So this just a little bit of straightforward algebra to get to that line. And then x squared plus y squared is equivalently, that's the square root of z. So that's how I got the z equals the square root, 1 over the square root of 2. So what that means is we're sitting up here at a height of 1 over root 2. And the circle that's given at that height is x squared plus y squared is equal to 1/2. So it's a circle of radius 1 over root 2. Okay, so that means the domain we are integrating over so what are the x and y values we're going to be integrating over? That's that region in the plane down below. That's going to be a circle. Well, circular disk, I should say. The circle is the one-dimensional curve around the outside. The disk also includes the center. That's the difference between a disk and just a circle itself. The circle is the boundary of the disk. So we've got 1 over root 2, 1 over root 2, indicating the radius there. And so this is the footprint of our region, if you will. It's the footprint down here in the xy plane. So our region is above that, and it's trapped between the sphere and the cone. So this is best described in polar coordinates. It's a circular disk, so it's best described in terms of polar coordinates. What is our description of it? Well, our r value is trapped between 0 and 1 over root 2, and our theta value is trapped between 0 and 2 pi. So that's the first thing to observe. But now we've got our region that we want to integrate over. That's our region in the plane we want to integrate over. So I'll separate off. Now we're ready to do our integral, our volume integral. So what is our volume? Our volume is going to be, let's integrate over that region. So I'll call this region, let's say, maybe I'll call it capital D for the domain we're integrating over. So we're integrating over capital D of the, now there's a couple of things we have to keep in mind here. We want to find the area or the volume between the two. So if I integrate over this domain of the sphere, which is the square root of 1 minus x squared minus y squared, that gives us essentially the volume of the whole thing underneath the sphere all the way down to the plane. But I want to remove the stuff that's underneath the cone. So I'm going to take away what's underneath the cone, which is the square root of x squared plus y squared. And that's going to be integral, an area integral. So D, integral over the region D with respect to the area. Okay, so that's the integral we want. Now we can go ahead and fill in our individual limits of integration. We're going to use polar coordinates. So our theta is going to go from 0 to 2 pi, as we've indicated down below. Our r value is going to go from 0 to 1 over root 2. We've got our first function, square root of 1 minus x squared minus y squared. That becomes a 1 minus r squared. we've got our second function, which is x squared plus y squared, square rooted. So x squared plus y squared is r squared, square rooted is just an r. And then we get our r dr d theta. So that was converting to polar. So we've converted our integral to polar coordinates now. And now we can go ahead and integrate. One of the things to keep in mind is what we are integrating over is a polar rectangle. And that means just our limits of integration for r and theta are constants. So because we're integrating over a polar rectangle and our integrand, our function in the integrand, doesn't depend on theta, means we can split this up into the product of the theta integral and the r integral. 0 to 1 over root 2, 1 minus r squared with an r out front, and then minus an r squared dr. So now we're in the realm of just having to compute two integrals from calculus 2. So the first one becomes just a 2 pi, and the second one, well, the nice thing about when we do the change to polar coordinates, we got that extra r coming in, and that means that this first integral, the r times the square root of 1 minus r squared, that's a nice one because we can use substitution on it, because there's a derivative of the inside function, the 1 minus r squared, sitting right on the outside. So this would be a 1 minus r squared to the power of 3/2. And then I just do a mental check. What do I have to put out front in order for it to give me a derivative of r times the square root of 1 minus r squared? So the derivative of this, 3/2 would come down, and then I'd multiply by a negative 2r for the derivative of the inside. So that means I would have a negative 3 out front, so I'll need a negative 1/3 to balance that. Okay, so just an antiderivative of this thing. If you want to do the full substitution, go right ahead and do that. And then the next piece is the antiderivative of r squared is 1/3 r cubed, and that's going to be from 0 to 1 over root 2. Okay, and then now we just substitute the limits of integration, and we can do a bit of reduction. So I'll leave that details for you. This is now a little bit of algebra and arithmetic. And what we get, root 2, there we go. Pi by 3 times 2 minus root 2. Okay, so that is the volume of the region of basically the amount of ice cream you can fit into this cone. It's in the cone plus the little ball up top that sticks out of the cone.
Professor?
Yes.
I had a question regarding the sphere.
Okay.
It says find the volume of the solid above the cone and below the sphere. How do you
Yes.
know the sphere is like peaking over the cone?
That's why we did the intersection here. So when we did the intersection of the two surfaces, what we found is that that intersection happens at a height of z equals 1 over root 2. And we know that the sphere is going to hit up here at a height of 1 because it's a sphere of radius 1.
Mm-hmm.
So the intersection of it with the cone is happening below that at 1 over root 2. And so it's happening down here somewhere at 1 over root 2. So we know the sphere's got to peak up above the cone.
Okay. Why are we taking the integral of z?
Why are we taking the integral of z?
Yeah.
Because we're doing a volume, right? So the idea is if we scroll back to, let's see, any of these calculations back here, the volume is we are basically integrating our function, which is our z values, over the region. So we've got some surface sitting in our space, and we've got some domain down below that we are integrating over, and so that's up to the surface here. This integral is representing the volume of this object. everything that's above that domain in the XY plane and sitting below the surface. And so that's our setup, is we are going to find the volume of the object that's sitting below the sphere and above the cone. So I need it to be trapped in between the cone and the sphere. So what I do is I find the entire volume underneath the sphere, which is all of this stuff.
Mhm.
And then I remove the stuff that's just sitting outside the cone, which is this stuff. And that leaves me with the stuff that's inside the cone and under the sphere.
What does it mean when it says under the sphere, like below the sphere?
So it means that the Z values are sitting underneath the Z values on the sphere itself.
Oh, okay. All right, thank you.
Yeah, so whenever it says below or under or to the left of or to the right of, it's meaning for that particular variable. So for the Z variable, we're looking at the sphere and we want it to be below the sphere. So our Z values have to be below the corresponding values on the surface itself.
Okay. All right, thanks.
You're welcome. All right, so we're going to head now into section 15.4. And this section's just about all the different ways that we could encounter double integrals in science. So I shouldn't say all the different ways, some other ways we can encounter double integrals in science and applied science. So right now, the way we introduced it was as a volume problem. We introduced the double integrals come up when you want to find the volume, but it doesn't have to be a volume. It can be other things that you're interested in. So for example, we could suppose we had a lamina. So a lamina is just like a thin plate. And so there's our shaded version of our lamina down below. It's a thin plate. It's not a circular plate. It's sort of this sort of bean-shaped plate. And what we have is that the density of this lamina differs depending on where you are. So it could have higher density in some locations, lower density in other locations. And what we call this is a non-uniform density lamina. And what we're interested in is figuring out what the mass of this object would be. If it was a uniform density plate, then we would just have to figure out what the area is and multiply that by the density, and that would give us the mass. But because we are assuming that it's non-uniform, this density function depends on where we are on the plate. So it's varying density as we move along the plate. Then the mass is not just going to be a straightforward product. The mass is going to be computed as an integral. And why is this? Well, the main idea is if we do want to find the mass, then we could chop this plate up into a bunch of thin little rectangles. And over each of these tiny little rectangles, we can assume that the density is constant, or at least it doesn't vary very much. So over one of these small little rectangles, we could take a sample point in it, which is at xij star and yij star. Once we take that sample point in it, we evaluate the density function, and that should be roughly the density of the region over the entire small little rectangle. And so what we have is that the mass of a rectangular element, so one of these small little rectangles, we chopped it up into a bunch of little rectangles. What's the mass of the small little rectangle? Let's call that Mij, the mass of the ith j rectangle is, well, we can think of the density as being constant over that entire rectangle. So when I sample it at a sample point, this would be the density over the entire rectangle, or at least a good approximation of the density over the entire rectangle. And so then we just have to multiply by the area of that little rectangle. And so this would be the ith j mass element. And then in order to find the total mass is the sum over all the mass elements. And taking the size of the rectangle to 0, so letting the delta x and the delta y get smaller and smaller and smaller and smaller, this becomes an integral. So we get a limit of a Riemann sum, or a double integral. And so the double integral would be, the mass is the double integral of the density function of over the area of our domain here. And I guess I'll call it a region. It was called a region R, so I'll keep it as an R. And so that's how we can compute mass, is we just integrate the density function. Okay, so this is one application of a double integral. We may have seen, so depending on where you took calculus 2, you may have seen this for example, for rods. We had in calculus 2 a rod of varying density along the length of the rod. To get the mass of the rod, you integrate the density along its length. We're just extending that now to, instead of a rod of varying density, we're now looking at laminas of varying densities over their surface. So that's, first indication of where we could see a double integral that doesn't represent a volume. There's no volume here. What we're just representing now is a mass as an integral of a density function. Another place, so same idea, we've got a lamina, and that's indicated by that blue object there. And we could be interested in what is its center of mass. So where would the balancing point be? And this depends on how the mass is distributed amongst this lamina. So in other words, it depends on the density. Where is it higher density? Where is it lower density? And taking into account how the mass is distributed around the lamina and its shape to figure out what its center of mass is. And the center of mass in this case is defined or given by these double integrals. So the x coordinate of the center of mass is 1 over the mass, and the mass is that integral we calculated above. So the thing to keep in mind here is that this is the above integral. It is the integral of the density function. And so it's 1 over the mass times the integral of x times the density function. And so that we also have a name for. This thing is, what this integral is doing is it's really sampling the density at all points on the lamina, and then also their proximity, in some sense, their proximity to some frame of reference. So that's why this multiplying by x. So it's what is the distance to the y-axis of this particular mass element situated somewhere on the lamina. And then you integrate over all of the mass elements times their distance to the y-axis. And so this is in some sense, a measure of how far mass elements are from the y-axis. And so we call this the moment. So this is called the moment about the y-axis. And we also have a notation for this. It's m sub y is equal to the integral over the region of x times the density dA. And then similarly, this one down here is the moment about the y-axis. The moment about the x-axis. Moment about x-axis. And so that's m sub x is equal to the integral over r of y rho x y dA. So these moments, in some sense, are sort of a measure of the tendency this object has to spin or rotate about the y-axis or the x-axis. And that, so if we think about the moment about the y-axis, so what's the tendency this object has to rotate about the y-axis, given how its mass has been distributed across it? It really depends on each sort of mass element on the lamina and its distance to the y-axis. And so that's what this integral is capturing, the tendency for it to rotate about the y-axis, or the tendency to rotate about the x-axis. And the x and y center of masses are those sort of balancing points. So let's go ahead and do a calculation. Yep, go for it.
Can you explain what you mean about the moment above the y-axis?
The moment about the y-axis. So we've got our y-axis here, and we've got, let's say, some sort of lamina. So this is our x-axis, this is our y-axis, this is our object here. And what the moment about the y-axis is, in some sense, the tendency this thing has to rotate about it. So imagine it's very dense out here. Your plate has a high density there, but it's a low density, you know, closer to the axes, and maybe it's high density here, but low density in other places. So the density is varying. So I pick a point on my lamina, somewhere where it's very high density. And what is the tendency for that point to rotate about the y-axis? Well, there's sort of a torque that's going on here, right? This point, if we imagine sort of it now being under the influence of gravity being rotating around the y-axis, that point, high density point, so there's a lot of mass packed in that point. It's a far distance from the y-axis, so there's a high tendency for it to rotate around the y-axis. In other words, it's going to generate a lot of torque around the y-axis. But other points, you know, lower mass points, lower density points on the surface, giving rise to lower mass points, closer to the axes, they're not going to generate a lot of torque. And so what this moment is in some sense trying to capture the amount of torque this object is going to exert, or the rotational tendency it has to rotate about the y-axis. That's what the moment about the y-axis is. It's a measure of the tendency for it to want to rotate around that axis.
That makes a lot of sense. Thank you.
You're welcome.
Is that the same moment as in like moment of inertia, or like moments in statistics?
So the moment, it is, yeah, in some sense. So the moments come in many types. So there's the first moment, the second moment, and then there's higher moments, third moments, fourth moments. What those numbers refer to is the power on the x that's in front of that density function. So right now we're talking about first moments. So I'll write the word first here. So this is the first moment about the y-axis, and this is the first moment about the x-axis. And the first moment is like the analog of a torque. It's in some sense trying to capture the rotational tendency. What the moment of inertia is, that's the analog of mass. So mass in linear motion is you know, a quantity that's going to determine how you accelerate under a given force. So there's a relationship between the mass of an object and the force applied to that object, giving an acceleration. So Newton's laws of motion, force equals mass times acceleration. So what mass is in some sense, it's a measure to the resistance, if you will, of the object to change motion or to accelerate under a given force. So the higher the mass, the more force you need in order for it to change its acceleration. And in rotation, the rotational analog is if you've got an object that's spinning, what is the concept that captures its resistance to want to change its angular acceleration? And it's no longer the mass. What it is in some sense how the mass is distributed about the axes of rotation. And in that case, it's really about how it actually turns out to be. It's about how the mass is distributed about the axis of rotation, in particular, the square of the distance the mass is from the axis of rotation. And so this is what's known as the moment of inertia, or what's also called the second moment, which is x squared rho of xy, the integral of x squared rho of xy. And so that's where moment of inertia comes in. It's the second moment. So that's actually, we're going to get to that on one of these pages. Here it is, moment of inertia. And there's a square there. So this is also known as the second moment. The second moment, because of that square there. So we'll get to that in a little bit. But the nice way you can sort of capture these ideas sort of very succinctly is the first moment is in some sense related to torque, the idea of sort of, the tendency to want to twist or rotate about an axis. And the second moment, or the moment of inertia, is a measurement of the rotational analog of mass. So the quantity that prevents you or tells you how your rotational acceleration is going to change under a given torque. Right. Yep.
Another question. Sorry to cut you off. It's about the M.
Up here, is that what you're?
No. Down.
Down?
Yeah. You see
Okay.
the circled M in blue?
Yep.
Yeah, you said it's above the integral. What does that mean?
The integral above. That one.
Oh, the above integral. Oh, okay,
Yeah.
okay.
Yeah.
Okay, thank you.
So I'll jot it down here. It's the above integral. In other words, it's the integral of just the density, xy dA over the region R. In other words, I just wanted to draw your attention to the fact that it looks like the center of mass is just one integral to compute, but it's not, because that variable M is another integral. So it's really the ratio of two integrals here. So if I look at the center of mass, the x center of mass, it's really the integral, well, I should say it's the first moment about the y-axis. So that's this integral here, x times the density, divided by the mass, which is another integral. It's the integral of just the density. So to find the x center of mass, we need to take the ratio of two integrals. The first moment integral over the mass integral.
Is the mass integral the 0th moment? It's technically x times 0.
Yes, it is. Yes, it's a good observation. Yeah, that would be the 0th moment. All right, so let's have a look at this problem. Find the mass of the planar lamina that occupies the region bounded by x equals 0 and this parabola that's flipped upside down. So let's sketch the parabola first. It's going to be a parabola that looks like this, which has our x-intercepts of -2 and 2. And so that's our y equals 4 minus x squared. And it's bounded by this parabola and the x-axis. So that means it's this region here. So there's our lamina. So that's our disk, if you will, or our plate. I shouldn't say disk. That's our plate, our oddly shaped plate. And we have a density function for this lamina. The density function, as given in the question, it's using delta to denote the density function. Above, I used rho, but here we're using delta. The density is given by the y-coordinate of the point you're at. So in other words, the more you move upwards along this lamina, the higher the density is. So it's highly dense up near the top, low density near the bottom. And so if we're thinking about where a center of mass could potentially lie, well, since the higher the density is, the further you move up, I'd expect the center of mass to be higher up the y-axis than it would otherwise be if it was a uniform density object. And then we'd also have to figure out what the X center of mass is. So in order to do the center of mass, or the centroid, as I mentioned above, there's really two integrals embedded in that formula. One is the mass integral. So let's go ahead and compute the mass first. The mass is going to be the integral over this region. I'll leave a little bit of space for my integrals so I can put the limits of integration up top of our density function. And we've got a couple of d's that we're going to be having to fill in. So I've left the spaces here because we want to figure out whether we want to integrate with respect to the x-axis first or the y-axis. So is it vertically simple? Is it horizontally simple? Well, if I draw a vertical line, then I've got an expression for the curve on the top and an expression for the curve on the bottom. The top curve is 4 minus x squared. The bottom one is just x equals 0. And so this looks like it's going to be a vertically simple region. If I wanted to do the integral along the horizontal direction, it means I'd have to, for any given y value, I'd have to figure out what x is in terms of that. That would involve finding square roots or rewriting the function. So what am I saying here? I'm saying that when I'm looking at these boundary curves, if I was to isolate x in terms of y, so that would be a square root of 4 minus y. That would be this curve here. But then I'd also have the other side that would be an x is equal to negative square root of 4 minus y. And I need to use those two things if I'm going to integrate with respect to y as the inner integral, and then x after. And so, you know, these are the things that I factor into my decision. Is it vertically simple or horizontally simple? Well, if I integrate in the vertical direction first, then everything's nicely expressed. So we're going to go the integral in our vertical direction dy. The y values range from 0 up to 4 minus x squared. And then to sweep out the region with the x values, they just go from -2 to 2. And so there's my setup of my integral. That becomes the integral from -2 to 2, the integral from 0 to 4 minus x squared, and the density is just y dy dx. And so there's our integral. We're
Is it supposed
integrating.
to be x equals 0 or y equals 0? Here's the y-axis, right?
Yeah, so we're thinking about this particular pink line here. And how do I, for a given x value, how do
your
I?
bounding region. It says the region is bounded by x equals 0.
It is bounded by x equals 0. That's the x-axis. Oh, sorry, x equals 0 and, oh yeah, sorry, I see what you're saying now. Yes, you are absolutely correct. That should be a y equals 0. Thanks for that. Exactly, that was a typo in my question. I was working with it from y equals 0, but you're right. I had a typo there. So yes, y equals 0. So in other words, this is one of the bounding curves, and then this is the other bounding curve. Thank you very much for pointing that out. Okay, and so now we're at an integral where the inner integral is integration of y, and then the outer integral is our x integral. So let's just have a look at our inner integral would be 1/2 y squared 0 to 4 minus x squared dx, or in other words, the integral from -2 to 2 of 1/2 4 minus x squared dx. And there's another square out there, so 4 minus x squared all squared dx. And you know what, as you go through these, so this is not our first course in integration. You've done integrals in your Calculus 2 class. So you can start to, you're probably a little bit more relaxed when you're doing these integrals. So you can start to look for time-saving devices. So for example, if I stare at this integral and I just look at it, go, well, I'm integrating from -2 to 2. So I'm integrating over a symmetric interval. And my function is an even function. The only place x appears is under an x squared. So it's an even function over a symmetric interval, so I can exploit symmetry here. So I can use symmetry and say, well, I only need to integrate over half of the region and then just double my result. So I'll integrate from 0 to 2 and double my integrand, or double the result, so I can get rid of that half in front. And that's just using symmetry. And then from there, we can go ahead and compute the integral, and I'll just write down what it is. It's 256 over 15. So that's nice, because then when my limits, I evaluate at my limits of integration, one of the limits is 0, which is always easy to evaluate at. Next thing we want to do is we want to go ahead and compute our centers of mass. So again, with this, we want to maybe take a step back and just think, can we do any time-saving devices? Because we know, can we notice any symmetry? And so what do you think? What should x bar be, the x center of mass?
0.
Yeah, it's 0. It's 0 because the region that our laminar plate is symmetric about the y-axis. But not only that, our density function is also symmetric about the y-axis. So this is due to symmetry of both the region and the density function. And if you want to check, you can go ahead and you can actually just work out the integral. I'll leave it to you to check. But yeah, you can work out the integral and you'll get that it's symmetric, and therefore the integral turns out to be 0. The y center of mass is 1 over m times the x moment. So this is 4 minus x squared. So everything's pretty much the same as above, except now it's y times the density function of xy dy dx. Or in other words, the integral from -2 to 2, 0 to 4 minus x squared, y squared dy dx, because the density function is y, and we are having to multiply that by y as our new integrand. And again, now we're an exercise in integration, so I'll leave the details of integrating to you, and this becomes a 16 over 7, or approximately 2.29. Why do I want to write down approximately 2.29? Because once I found 16/7, I'd like to know, where is that roughly in my diagram? So I know this is a height of 4 up the y-axis. That's where our parabola sort of ends. Its vertex is up there at a height of 4. And 2.29 means we are just above halfway. So we are somewhere around here. So maybe I'll put this in a different color. And so that is going to be our center of mass. It's above halfway up. If this was a uniform density lamina, that means at every point the density is the same, then we would expect the center of mass to be closer to where there's more stuff. And that's so at least the y coordinate of the center of mass. So it should have been down lower because there's a lot more bulk down below. But because the density is varying and it's higher density up in the region above, then the density, being the higher density up high, it has shifted our center of mass up higher along the y-axis. So that's just something we can, use as a sort of a double check to see if our calculations do make sense.
Wait, so Professor?
Yep.
Here is x bar equal to 0 because there's no x value in the density
Correct.
equation?
Yeah.
Okay, so that's why.
Yeah, and it could still be the case even if there was an x value in the density. It's just because it's symmetric. So if the density function was, for example, y times x squared, because the density function would be symmetric around the y-axis with the x squared value. It means if you're on the right-hand side of the y-axis or the left-hand side, you're getting the same value. So it just means your density is symmetric about the y-axis. So it wasn't the fact that x was missing, though that made it easier to tell. It was the fact that the density function was just symmetric about the y-axis in general. For any given positive x, y point, the density was the same for the negative x, comma, y point.
What do you mean by symmetric over the y-axis? Does it mean like if you flip it, it will be the same x values? Is that what it means?
Yeah, it means that the density of a point here, x, y, and the density of this point are the same. They have the same density. And that's
Oh,
true
Professor.
for all points.
But isn't their x values different?
Their x values are different, but their densities are not, because the density just depends on, in this case, the y value.
Oh, okay, I get
But
it now.
even if let's say the density function was yx squared, then those 2 points would have the same density. Even though one of them had a negative x value and the other one had a positive x coordinate, their densities
Yeah.
are the same. So it means that not only do we have symmetry of the region, we also have symmetry of the density function itself.
Okay, yeah, makes sense now. Thank you.
You're welcome.
Professor, the density has the unit kilogram per meter squared, but y has the unit meters. So how can we equate density to y?
Oh, you're asking about a unit
Yeah,
here?
yeah.
Yeah, so this is the density at a given point is given by its y coordinate.
But they're like
So
unit different.
Yeah, so for example, at the point, let's say, well, maybe I'll make sure we get in there. So at the point 1, 2. So at 1, 2, the density at 1, 2 is given by 2, and then the units of density. So
Okay, thank you.
yeah. Okay. So let's now have a look at another application. This one's a bit of a blast from the past, but I want to connect it with the current materials, in particular center of mass. So this blast from the past is we learned about how to compute volumes of solids of revolution in Calculus 2. And this was probably one of the examples. If you did it at SFU, Math 152 at SFU, you probably would have done the volume of the torus using either the disk or the cylindrical shells method. And you get a volume of 2 pi squared r, little r squared, big R, where little r is the radius of this small circle in the diagram, and big R is the radius of the torus. And so these two quantities, big R and little r, combine together to give us this formula. And we can go ahead and we can compute this. So to compute this, I'll just indicate how we did it. We used the shell method. And in order to do the shell method, what we ended up doing was we looked at just half of it. We used symmetry. We took the upper circle. So I'll just indicate some of the distances here. That was our x-axis, our y-axis. We took an upper semicircle and then we rotated it about the y-axis. That gives us half of the volume, the upper part of the torus, and then we can just multiply by 2 to get the lower half as well. And the things we needed to know in this case was the equation for this curve, and that would have been x minus big R squared plus y squared is equal to little r squared. So that's just that circle shifted over to have a center of x equals big R and y equals 0. But since it's an upper part of the curve, we could solve for the positive square root for y. and we get little r squared minus x minus big R all squared. So that is our curve, that upper curve, or that upper semicircle. And then the shell method to get the volume, the shell method is we integrate over the x values, and our x values are going to go from capital R minus little r to capital R plus little r. And then 2 pi, so since we're using the shell method, it's 2 pi times the distance our given slice is. So we look at a slice. What's the distance that slice is from the axes of rotation? The distance that slice is will be its given x coordinate. And we let those x coordinates sweep out the values from big R minus little r to big R plus little r. And then we need the height. So it's 2 pi times the distance to the axes of rotation times the height of the cylinder that that slice is going to create. And the height is given by the square root of r squared minus x minus big R all squared, and that's dx. And so that's our volume we end up getting. And maybe I'll just indicate here, this might be a reminder to many of you. You might at this point remember what we did exactly in Math 152 to do this, or you may be thinking, oh, I vaguely remember this, but I don't remember how to do this integral. What we ended up doing at this point was we just made a substitution. So we just said substitute variable u for x minus big R. So du becomes dx, and our limits of integration, which were x is equal to big R plus little r, that becomes u is equal to little r, and x is equal to big R minus little r, that becomes u is equal to negative little r. So once we do our substitution, then we get our volume is equal to the u integral from negative little r to r, 2 pi, and then x becomes u plus big R. So that's part of our substitution. That x changes to u plus big R. And then we get our, oh, this becomes a u now. Then we get our integral becomes r squared minus u squared and du. So we did that substitution just to simplify what was going on underneath the square root. And in fact, we get a whole bunch more simplifications that turn out to make this integral quite straightforward to do. So I'll bring out the 2 pi. I'll join up the u with the integral, and then I'll also join up those two. So I'll basically distribute across and form 2 integrals. And with that second integral, the big R being a constant can come out front. So that's negative r to r square root of r squared minus u squared du. And so we end up getting these 2 integrals. And the observation is that this is a odd function being integrated over a symmetric interval. So this is 0 by symmetry. Maybe I should just say 0 since it's an odd function. On the other hand, this integral here, that's the integral of a upper semicircle over the interval negative r to r. So this is basically half the area of a circle of radius r. So this is equal to 1/2 pi little r squared. And so we get our result of 2 pi times big R times 1/2 times little pi r squared. And I've forgotten one more thing I've got to add in. Remember, I use symmetry right from the start. And because I use symmetry right from the start, there's actually a 2 in front of everything. because I only did the integral involving the upper portion of the torus. So there's actually a 2 all the way along here, another 2 there. And so now we get the result of 2 pi squared, little r squared, big R. And that is our integral. Now, this is calculus 2. So now where does it fit in with calculus 3? I'll just finish up here and then we'll do the rest of it next day. How it fits in with calculus 3 is a lot of times students observe in calculus 2 that this looks an awful lot like pi r squared, and then a 2 pi r, and then another big R. So something like this. Let's see. Oh, not a little r. There we go. A lot of people in calculus 2 go, wait a minute. That looks a lot like pi r squared times 2 pi r. What's pi r squared? Pi r squared is the area of this circle. What's 2 pi r? 2 pi r is the distance that circle got rotated around. So if I imagine slicing this torus open and unraveling it, making it into a cylinder, it's basically a cylinder whose cross section is pi r squared and whose height is 2 pi r. And so we see that this formula really just has some connection to the cross-sectional area times the distance it was revolved around. And it turns out that that's actually a general statement, and that's called the first theorem of Pappus, and it's related to the center of mass, and we'll pick that up next day. See how that comes into play. All right, so I'll stop the recording.